We'll have a test tomorrow over what we've done so far, chapters 1, 2, and 3. And more or less, chapter 1 was kind of an algebra review. We did some of those things in chapter 2 and chapter 3. So it's more or less chapters 2 and 3 that we'll be focusing on. But some of the basic algebra skills we looked at in chapter 1 will show up in some of these. So today we'll talk about what to expect on the test. First of all, there are 20 problems. I do grade them by hand. I look at, first of all, whether they're right or wrong. If they're right, you get 5 points for that problem. If it's wrong, then I look through what did you do wrong, and you could either get, well, if you show some work and show that you know mostly what's going on and maybe make a little mistake, I'll count 1 off. Then if you kind of have an idea but make a somewhat one major mistake, then I'll probably count 2 off, and so on. And if you show me nothing or show just an answer that's wrong, there's 5 points off. So make sure and at least show me a little bit. Some of these, there may not be a lot of work to do, but at least show me something that, in case you punch the calculator incorrectly, well, don't punch your calculator, but if you punch a button wrong and you get a wrong answer, then if you show me some work, you at least get a little bit of points for showing me you know something about it anyway. Hopefully you know something about it. But time-wise, you should be able to do the whole thing during class time. Now, I do allow you more time if you need it, but I do not allow you, I will not write an excuse for you to be late to your next class. That's going to be your responsibility. Is it worth spending another 10, 15 minutes on the test and being late to your next class, if that happens to be the case? Or if you want to start early, that's fine too. Come to my office if you want to start early. There is a class in here before ours. So that's an option. That's up to you. But you should be able to get it done in the regular class period. The problems on the test will be similar to your worksheet problems.
So if we study our worksheets, we're going to be okay?
Yeah. If you know how to do the problems on your worksheets, then you should be fine for the test. And we'll kind of go back to maybe the beginning or close to the beginning and remind you of what you were doing. At this point, sometimes we forget, we haven't seen everything we've done way back at the beginning, 3 weeks back now. So, doesn't sound like a lot, but we've covered a lot of ground in here. One main topic we hit especially hard in chapter 2 is limits, calculating limits, and we looked at a lot of different procedures, a lot of different algebraic procedures for computing a limit. The most basic one if we have something like this, what should you do very first thing to see what the limit is? Okay, just plug it in and see what we get. And in this case, we'll have x approaching 2. Now, technically, that does not mean when x equals 2, but that's the easiest, quickest way to see what the limit is just put in 2. and as long as it's a valid answer, a valid result, then that's going to be the limit result. So we'd have what? 4 minus 4 plus 4, 4 over 3. That limit will be 4/3. Now later on we talked about continuous functions and so forth. We could come back to this and say, well, this function is continuous at x equals 2, first of all, because it's defined, f of 2 is defined, the limit exists, and f of 2, what we did right here, will equal the limit value. So that's why the very first thing in calculating a limit, just plug in the number and see if it works. Now the problem would be if this was x minus 2 in the denominator. Now a lot of what we do would depend on what's in the numerator, but one major problem we have here, even just seeing the x minus 2 in the denominator, is that 0 in the denominator. Now, if we get something other than 0, I'll just put not 0 divided by 0, what can we say about this limit? Okay, undefined, does not exist, which you can abbreviate DNE. Okay, so, but that's only if the numerator is not 0 and the denominator is 0. Now, if it's 0 over 0, then we have much more work to do. 0 over 0 is that indeterminate form, and we can maybe find some different algebraic ways to simplify the function, rewrite it to where we can get a value. So, and of course that's going to be, most of the problems on the test will be that 0 over 0, something like that. But do keep in mind these two somewhat quick ways to evaluate limits. What about this one? What would we do to evaluate or to find this limit? Well, right off plugging in -1 for x, what do we get? Okay, there's our 0 over 0. So we do have more work to do. In this case, what would we do? Okay, factor, and we factor top and bottom. Top factors into that, and bottom factors into what? How about the other way around? Nope. I said the other way around, and then oops, that's not what I wanted.
It'd be -2 and then plus.
Yep. Okay, hang on. Okay, well, let's rewrite that as x minus 2 and x plus 1. Sometimes our factoring gets a little tricky. Sometimes it's a little bit easier to see what it should factor into. We have the x approaching -1. Well, we want to get rid of the x plus 1 in the denominator to get rid of the 0 from the denominator. So that can sometimes help factor. So we cancel our x plus 1s. Now, as we plug in -1 for x, we'll get, well, -2 divided by -3, which would turn out to be a positive 2/3. So that limit would be 2/3. Okay. Questions? What about this one? When we plug in 2 this time, what do we get?
0 on the bottom.
And we also get 0 on the top, right? Oh, that's what I was shooting for. Okay. So once again, we have some more work to do, but this time it's not a factoring problem. With the square root in the numerator, what do we have to do to it?
Conjugate.
Okay. We're going to do what we would call rationalize the numerator, which means we multiply by the conjugate. So the top, we would have the original numerator times its conjugate, which would be that square root plus 1. We still have the x minus 2 in the denominator, and if we multiply something by the numerator, we have to multiply that same thing by the denominator. Technically, we're multiplying by 1, so we're not changing the value, but we will be changing the form. Now, as we multiply this out, FOIL the top, square root times the same square root, we'll have x minus 1, then plus 1 times that square root, minus 1 times that same square root. So the square roots will cancel each other out. And then don't forget the lasts, negative 1 times 1 will be another minus 1. And all over, didn't leave enough room, I'm afraid. Actually, we kind of fit it in there. Well, the numerator turns out to be what?
X minus 2.
Okay. And we have that factor x minus 2 in the denominator as well. So now we can get rid of those. And we're left with what?
Square root of x minus 1 plus 1.
Okay, I guess we'll be able to take care of the limit now. Now the numerator will still have a 1 up there. Okay, don't forget we're x minus 2 divided by x minus 2 is 1. Sometimes we think, well, we got rid of everything, there's nothing left. It's a 0, but it is 1. And then we have that square root of x minus 1 plus 1 in the denominator, this part right here. And now we can go ahead and plug in the 2. We'd get, what, 1 over square root of 1, or 1 plus 1. So we get a value of 1/2 for that limit. So square roots, evaluating limits that way, rationalize your numerator, a lot of algebra, simplifying, and then finally we're able to plug in our x value. Questions there?
How did you get 1/2?
One more kind of special type of limit that we ran into, this complex fraction. And again, the first thing we should look at when we plug in 4 for x, what do we get?
0 over 0.
Okay, once again the 0 over 0. So we have more work to do. It's not that simple, unfortunately. So there's actually a couple different ways we could approach this one. What's one way that first step we need to take? Okay, we need a common denominator, looking at our numerator part, and looks like one factor will be the x minus 1, the other factor will be 3. So 1 over x minus 1, we need to do what to it to get our common, oh man, that's a x minus 1 there. What do we need to get our least common denominator? Or what do we need to do?
Just cross multiply.
Okay, we'll multiply by 3 over 3. And yeah, with the 1/3 to get our 3 times the x minus 1, multiply it by x minus 1 over x minus 1. So the first numerator turns out to be a 3. The second numerator would turn out to be the x minus 1. And, oops. We would be subtracting that. Yeah, we need to be careful with that part. So we'd have 3 over the least common denominator minus, and then our x minus 1 over the least common denominator. Now, you may be looking at this as cross-multiplying, which technically that's not what we'd call it, but if that works for you, that's fine. We are essentially multiplying the 3 over here and then the x minus 1 over here. What you really have to be careful with, though, is this right here. We're combining this. We do have a common denominator, and we would be taking 3 minus the quantity of the x minus 1. Not just minus x minus 1, but minus that entire quantity, which will actually change that to plus 1 there at the end. So 3 minus x plus 1. Okay. Now, this problem gets so long, we need to remember what we're doing. That is the overall numerator for the big function we started with. And then all of that would still be over the x minus 4. And at this point, a couple things. Well, first of all, we could combine 4 minus x in the top. The x minus 4 in the bottom, if you want to think of that over 1, we're dividing fractions, so we can invert and multiply. Take this fraction divided by or multiply by the reciprocal of our bottom. And then, well, we're still not quite exactly to where we can cancel things. We have the 4 minus x in the top, but an x minus 4 in the bottom. What could we do to kind of change one part to get it to cancel? Okay. We can factor out a negative 1. Negative x plus 4, if you want to rewrite the order, then factoring that negative 1 out will get us a positive x minus 4. And so that would become our numerator. X minus 4 would cancel. And we have the negative 1 over 3 times the quantity of x minus 1, which now we need to apply our limit.
Since we factored out a negative 1 on the top, do we have to do that to the bottom?
No. We shouldn't do that on the bottom because we factored it out on the top to make what's left the same as the bottom. Okay. And now we can go ahead and plug in our 4, and we'd have what? Negative 1 over 3 times 3, or negative 1/9. These problems are a little too long to fit all on this one screen. Sorry about that. Now, we also looked at some problems involving graphs, and we talked a lot about some different things with those graphs. One was calculating limits based on the graph. And in this case, let's take a look at The limit as x approaches negative 1. What can we say about that? Okay, that one does not exist because the limit x approaches negative 1 from the left is what? Okay, from the left, we're coming up here. Okay. And the limit as x approaches 1 from the right, or negative 1 from the right, what does that equal?
0.
Okay, that would be our 0. So for a limit to exist, they have to approach the same function value from both sides. Okay, one approaches 2 and the other side approaches 0. Now, is the function defined at negative 1? Okay. F of negative 1 is what? Okay, because of the solid dot, that's equal to 0. Okay. And because the limit does not exist, we talked about continuity, we would have a discontinuity at negative 1 because of that limit not existing. Okay. The function value is defined, but the limit does not exist, so we have a jump discontinuity or non-removable discontinuity. Now, any other point that would cause a problem with continuity? Is this function continuous for all other x values? Okay, it's discontinuous where? Okay, at x equals 2. Okay, we said it was discontinuous at x equals negative 1 as well. Why is it discontinuous at x equals 2? Okay. F of 2 is undefined. Okay. Now, we have an open circle there. What's that tell us about the limit as x approaches 2?
It's going to touch it there, so it's going to exist.
Okay, the limit is going to exist. It's approaching the same value from both sides, and in this case it's negative 2. And again, I'm trying to get too much on this little screen, but bear with me, please. So the limit exists, but because the function value is undefined, then we have discontinuity. Now, what if we made f of 2 defined? Let's say we put a solid dot up here. Okay, now this part was before that. Now f of 2 is defined, but do we have discontinuity still? Yes. The third condition, the main condition, the limit value must equal the function value. And even though if we did put a solid dot here, the function value would be defined, it's still not going to be continuous because it's not equal to the limit value. Okay? Now, these two different points of discontinuity, one of them has a special name. Which one would that be? What can we say about this one? Okay, it's a removable discontinuity because had we decided our solid dot should go in this spot, then we'd have continuity with that one additional condition. So we say that's a removable discontinuity. If the limit exists, basically you're going to have a removable discontinuity if we're not continuous at that point. Okay, so lots of different things about graphs, limits, continuity. Yeah, question?
So to be continuous, the limit value must equal function value?
Correct. To be continuous, the limit value must equal the function value. And we can see that, let's just pick out the point here at x equals 0. F of 0 would equal -1. And the limit as we approach 0 from both sides would also be -1. So those aren't near as interesting points as these discontinuous points, but that is the definition of continuous when the limit equals the function value at that x. Okay. Well, after we introduced the idea of limits, we started looking at some applications, average velocity, and then we jumped into instantaneous velocity. So be able to calculate average velocity or average rate of change, average rate of change is about as general as I can get. The idea, though, average velocity, the change in the distance divided by change in time, or the change in the y value divided by the change in the x value. Slope of a line, slope of a secant line could be thought of as an average rate of change. Now, that would be over 2 time periods, say from 1 to 2, or maybe it's a lot smaller, from 0.9 to 1, or maybe from 2 to 2.001. We could still calculate an average velocity, even as small as that interval is. But as the idea of that interval getting smaller and smaller and smaller, approaching 0, we start to look at instantaneous velocity. So we did a lot of problems with average velocity and then instantaneous velocity, position functions, and then we were already using what we call the derivative, but we defined the derivative after we went through the instantaneous velocity problems. The instantaneous velocity is an application of the mathematical operation of the derivative. So, introduce the idea of the derivative with the instantaneous velocity. Then we said, okay, what is the derivative of a function at x equals 1? Or what is the formula for the derivative of a function? And we also saw that it could represent the slope of the tangent line as well. Okay. And our calculation of that would be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That was our definition of the derivative. We could use that formula to find the instantaneous rate of change at a particular point. Say if x equals 1, what is the instantaneous rate of change or instantaneous velocity of a position function. Or we could put the 1 in here for x. And most of this is algebra, lots and lots of algebra, lots and lots of little or steps that could allow for little mistakes. So be careful. Just a little warning there. Of course, you remember all those little mistakes you were making, so don't make them on the test. Or at least try not to. I know that's easier said than done, but anyway, lots of algebra, and then finally we get to a point where we can apply the limit as delta x approaches 0, whether it's a specific number, finding the slope of the tangent line at a certain point, instantaneous velocity at a certain time, or if it's just the derivative of the function. Everything would cancel out down to maybe 2x plus 3, something like that. So that was the idea of the derivative. And then using the derivative, we looked at some applications of that with, again, slope of the tangent line, position, given a position function, the derivative represents the velocity, instantaneous velocity, and motion of an object. Earlier this week we looked at the motion of an object in a horizontal line. Okay, so be able to work through any of those applications. Some of the problems I may actually even give you the derivative as well as the function and say, well, now knowing the function and the derivative, at what time is the velocity equal to 0, or worded on the motion of an object worksheet, at what time does the object stop? Okay, that's where the derivative is 0. And all sorts of questions we could come up with on position and velocity. And then finally, the very last we looked at were the derivatives of those special functions. Which was like the 1 over x. Well, setting that up, by definition, f of the quantity x plus delta x, we'd have 1 over the quantity x plus delta x minus f of x all over delta x. And to solve that, that goes back to our complex fraction. We did some limits like this. We'd have to find a common denominator, combine the numerator into one single fraction, and work through the simplifying that way. And the other special type of function was our square root, which, as we look at that in the definition form, we'd have the square root of x plus delta x minus the square root of x all over the delta x. So here we would have that limit that we looked at just a little bit ago with square roots in the numerator. Rationalize your numerator and work through that, and you could show what the derivative of the square root is. Now, a few of you know some shortcuts on this, but when it says find the derivative of these special functions, or however it's worded, you'll need to go through the definition. I think it does say use the definition to find the derivative. So can't just use your shortcuts. You got to show me the work using this nice little formula. Next week we'll get to start looking at the shortcuts, and everybody gets to use them, but not this week, not tomorrow. So, okay. Questions?